Physics. My name is Mr. Connolly, and we've been doing Newton's laws. We did Newton's first law, and as a recap, Newton's first law basically says object in motion wants to stay in motion, object at rest wants to stay at rest. We labeled it inertia. Then we moved on to Newton's second law, which said, basically, that if you have a force, it will cause an acceleration, and the force and the acceleration will be in the same direction. We did a bicycle demo relating to that one. Well, today we're going to move on to Newton's third law. Newton's third law. And Newton's third law says this. When one object exerts a force on a second object, the second exerts a force on the first, which is equal in magnitude but opposite direction. Now, the example that most quickly comes to mind for this, because I've seen it several times on the Regents, is a car is driving down the road and a mosquito or a bug hits the windshield of the car. What happens to the mosquito or the bug?
Splatters.
Boom, it gets splattered, it gets killed, right? But, how does that apply to Newton's third law? Well, did the bug supply a force into the windshield? Yeah. Did the windshield apply a force back? Okay, so you can see that there's forces going opposite directions, the bug and the windshield. But why would they be the same? Because didn't the bug just get blown up? Why would they be the same? Well, the bug only applied a little bit of force on the windshield because the bug's only little. And the windshield only had to apply a little bit of force back to the bug to cancel it out. So they are equal forces. Okay, let me give you another couple examples. I'm going to spin you around to the back here. A couple little quick demos. I want to be able to see this right here. Okay. So, the first demo is this. I got one of these, lab gloves. Or across the hall. Alright, so, if I take this glove and I just let it go at this point, it doesn't go very far. Well, but it goes. How is this glove being blown up and then going? An example of Newton's third law. Well, one force exerts on a second object, and then the second object exerts the same force back. How is that applying to this? What is exerting the force? Let's start with out of the glove. Joe?
The air is...
Okay, the air is going that way, if the glove went that way, right? The air is going that way. Well, what is the thing that's exerting the force back this way?
The air that's already in the room.
So, the air in the room all of a sudden decides to just push this way?
Yes.
Probably not. But if you think of it this way in your mind, there's air rushing out of the glove. What is it running into? Other what?
Particles.
Other particles, air, and other things that are here. There's stuff in the air that you can't see, and the air that's rushing out is ramming into that stuff. And what is that stuff doing? It's resisting that. It's pushing back. It's saying, whoa, I have, each of those little particles that you can't see here actually has inertia, back to the first law. And so each of those little particles that are all in the air here can provide some amount of resistance because they each have their own little inertia. And all combined, they provide enough inertia that this air can push off of them equal and opposite forces, and this thing can move forward. Does that make sense to you? Let's look at this one. This one is fabulous. This is, I got this out of a cereal box years ago. Are you able to see this? Yep. You're going to be able to see about that part out?
Not that part out.
Here?
Yeah, there.
Alright, it'll work, I think. So if you watch this, it's a little, get a little closer here. It's a little dog with a string and a mast hanging out the front of the dog. And this dog is incredible because when you let go of this dog, he starts walking and then, whoa, he knows every time to stop walking at the edge of the table because he's a magic physics dog. Let's watch again. The dog walks, the dog stops, as if he knows the edge of the table is there. How does this apply to Newton's third law? ideas. What is the force that's making him walk? Yeah, this mass thing is obviously kind of pulling him, like if you had a leash hooked to the dog, you kind of yank your dog along if it's not cooperating. So the mass is kind of pulling the dog along. That's force. Okay? And then the dog gets to here. What direction is that force pointing?
Down.
You can see that the ball, the mass, is hanging straight down, pushing straight down. So there must be an equal and opposite force, which is pushing straight up. I don't really see it. Okay? What is pushing straight up, though, is the actual table here. And the name for this table is called the normal force. So if you sit on your chair and your weight pushes down, then the normal force is the chair holding you up. Same with this situation. The weight is straight down, the normal force is straight up, and this table is more than stout enough to handle this tiny little dog, so it holds it right in place. Now how does this relate to Newton's second law? Go back to yesterday's lesson. Second law said if you have a force, it causes an acceleration. Is that happening here?
Yes.
Okay. There's a force caused by, the force of gravity. It causes an acceleration, so the dog walks this way. Now that the force is this way, why did the dog stop walking? Well, remember yesterday that the net force means when you add all the forces up, if you still have a number, it will cause an acceleration. But in this case, what's true about the table, the normal force, in comparison to this force pulling down? Yeah, and the table can withstand a lot more, you know what I mean? This thing's really light. The table's really strong. So when the force is this way, it pulls the dog. When the force becomes that way, now the table is stronger and it just won't allow the dog to get pulled straight down through the table. Because remember, the second law said the direction also matters. Does that sound good? Okay? So that is it for our amazing little space dog here. Let's zoom back up to the front. And I'm going to draw you a few pictures. The first one is, say someday you go skydiving. Here you are. You're enjoying your free fall out of a plane. And as you free fall, as you fall down, there are forces that are acting on you. Let's draw those as arrows. There's a force pulling downward. That's called the force of gravity. We abbreviate it Fg. It can also be called someone's weight. And there's another force. How do I know? Because when you first jump out of a plane, you fall faster and faster and faster and faster. Then you get to a point, and it's called terminal velocity, and you don't fall any faster. So at that point, if you're not falling any faster, then the force down must be counterbalanced or equaled out by a force up. What's that upward force called? Well, you can name it a lot of different things, but a lot of times people will call it wind resistance or something like that. So when you get to that point where you're not falling any faster, when these two are equal, the wind is dragging on you the same as gravity is pulling down on you, and you just continue to fall. Now notice when I draw my pictures, my arrows always start at the middle of my object and point outward. Okay? That's important for later. Let's do another example. Say you're in an elevator. Here you are in the elevator. And this elevator, let's say it's going up. And actually it's accelerating up. So it's going up, but it's speeding up as it goes up. And it's accelerating at 2 meters per second squared. And let's say the total mass that we're talking about here here of this system is 570 kilograms. Well, what I want to know is what sort of force does the elevator have to apply to make this happen? So I want to know what sort of force is being applied by the elevator. Question. Alright, so let's real quickly draw in our forces. What forces, what direction should the arrows point on this picture? Well, obviously, like I've said, there's always one arrow pointing down, and that arrow is called, everyone?
Gravity.
Yeah. So you got a force of gravity, just like my other pictures, my arrows start in the middle, they point outward. But in this case, since the elevator is going up, there must be an arrow that's pointing up, and the arrow pointing up actually must be stronger than the arrow pointing down because it seems to be winning, if you will. And what do you want to call that? Well, I already kind of hinted at it. Why don't we call it the force applied? Force APP. So you got the force applied up, and you got the force of gravity down. Now, the next step in this sort of problem, if I'm trying to figure out what the force applied is I got to set up a net force equation. So that says something like this. Remember from Newton's second law that F net is equal to m times a, but instead of setting it equal to m times a, I'm going to set it equal to the other forces in the problem. So I'm going to say F net is the applied force plus the force of gravity. And remember, I'm looking for this one. So if I can find the other two, I'm well on my way to solving this problem. Now I need to remind myself, just bring it back to the forefront of your mind here, that F net is the same as mass times acceleration. That was from Newton's second law. And I also want to bring to the forefront that the force of gravity, the weight, is the same as mass times acceleration of gravity. And so this equation and this equation both appear in the reference table, and we can actually now solve the problem. Because watch, all we have to do is we say, on this side, the mass, which is 570 kilograms, times the acceleration, which is 2 meters per second squared, is equal to the one I don't know, the F applied, plus the mass, which is 570, times gravity, which is a negative 9.81. Take a moment to look at that, check out that situation. Now when I solve, when I multiply this together, and pull this one over to this side, it ends up that the applied force turns out to be 6,732-ish. And so what this tells me is that elevator has to pull up with 6,732 newtons worth of force to make this actually possible. So that's it for today. Catch you next time. Physics.